All right, folks, welcome to Unit 3. This is the quantum atom. This is the fourth installment. And you are probably going to need a periodic table for this one. So if you don't have one handy, go ahead and pause the video and we will get started. So here we go. Last time we talked about the fact that there were specific rules that govern the positioning of the electrons around the nucleus. The Aufbau principle, we said, said that the electrons were going to be as close to the nucleus as possible. They were going to occupy the lowest possible energy levels. And the Pauli exclusion principle said that no two electrons could have the same energy level or the same four quantum numbers. In other words, they couldn't be at the same place at the same time and doing the same thing. And what we want to do today is we want to add another rule. It's called Hund's rule. And here's what it says. It says, in a subshell with multiple orbitals, no orbital may contain two electrons until each orbital of that energy level contains one. So let's take an example. Let's take nitrogen. Now, if you look at the periodic table, nitrogen has a total of 7 electrons. So where do we place them? Well, the Aufbau principle says you have to place them as low in energy as possible. So we're going to start with 2 electrons in the 1s sublevel. Now, those 2 electrons are represented by arrows that have opposite spins. So 1s, one spin goes one way, one spin goes the other way, right? So that's 2 out of the 7. The next 2 are easy as well. We've got 2 in the 2s sublevel, 1 up, 1 down. The problem comes in the next 3 electrons and where we place them. Well, we could place them so that I'll say 1 and then 2 and then 3 and then let's get rid of this one. And that would be the 3. But as it turns out, according to Hund's rule, that's not correct. Because Hund's rule says that you have to place these electrons as far away from each other as possible, right? You cannot have a second electron in any one orbital until you've had 1 electron in each of the orbitals. So we'll put those 3 here, here, and here. So we've got a total now of 7 electrons. 2 in the 1s, 2 in the 2s, and 3 in the 2px. Let me write px right here. This is py, and this third one is pz, just like that. So that's Hund's rule. So now what I want to talk about is electron configuration notation. Electron configuration notation is kind of a code for where precisely electrons reside around the nucleus of the atom. And orbitals are around the nucleus in a specific order. The problem is that the order is not necessarily consecutive, that there is overlapping in the orbitals. And so we need a way of determining where the electrons are. Well, there's a nice little mnemonic that you can use to help you to remember the order of electron filling. And here's how it works. You simply write on your paper 1, 2, 3, 4, 5, 6. You do that on your scratch paper. Then you stagger. You're going to go 2, 3, 4, 5, 6, 3, 4, 5, 6, 5, 4, 5, just like that. Then what you're going to do is you're going to put S next to the first column, P next to the second column, D column gets, third column gets a D, fourth column gets F, just like that. And that tells you the order of the filling. So you start right here. You start at 1s, just like that. And you go 1s and then you go up. So once you're finished on that line, you go back up and start again. So 1s, then 2s, then go back up. Then 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. So the next thing to remember is this. The next thing to remember is that S subshells hold 2 electrons. Okay? S subshells hold 2 electrons. P holds 6. So 2 for S, P holds 6, D holds 10, and F holds 14 electrons. So let's try a few very, very easy ones. So hydrogen has 1 electron only. Where do we put that 1 electron? Well, we can see from the table that the lowest energy level is the 1s sublevel, or the 1s orbital, I should say. So we're going to put it into the 1s. So hydrogen would have an electron configuration of simply 1s1. That's for hydrogen. How about helium? Well, it has 2 electrons. Its electron configuration would go, both electrons could go in that lowest energy level, it would be 1s2, just like that. So that's hydrogen and helium. Let's take a look at the 10 most or the lowest 10 electrons, 1 through 10. We've already said hydrogen and helium. Let's take a look at fluorine, for example. Fluorine would be 1s2, 2s2, 2p3. I'm just going according to the table, right? I can't have more than 2 electrons on s sublevels, but I can have as many as 6 on a p sublevel. By the way, this last column is the number of valence electrons. That's the number of electrons available for bonding. We're going to be talking about bonding in a couple of units now. So these are the electrons that are in the outermost level. So what we want to do now is we want to practice a few on our own. Let's start with scandium. Here's where you'll need your periodic table. Scandium is number 21 on the periodic table. That means that scandium has 21 protons, but it also has 21 electrons. Where do we place them? We're going to use the table to help us. And I don't think I can see the table and see these at the same time. Let me just try. Nope, can't do it. So you follow me on the table as I write these in. Ready? So here we go. Scandium, 21 electrons. So we're going to start with the 1s orbital, so that's 2. So 1s2, it can hold 2 electrons. Got a long way to go. 2s2, 1s2, 2s2, and then 2p. 6 electrons can be held by the p sublevel. 3s, so I'll put 3s2. 3p, so 3p, 6, just like that. Then 4s2, I can hold 2 electrons there. And now I go to a d sublevel. Scandium is in the d sublevel, so scandium would be 3d1, just like that. All right? So scandium's electron configuration notation is written right there. Cobalt, a little harder. Cobalt is 27, but at least the first 21 are written right above here for me. I'm going to say 1s2. I can speed up here a little bit. 2s2, 2p6, 3s2, 3p6. Follow me on the table. 4s2, 3d7. 3d7 this time. Okay? And then finally I'm asked about arsenic. All right? So arsenic's got a lot of electrons. It's got 33 electrons. Let's do it. Here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. All right? Again, P can hold 6 maximum, but we only needed to hold 3 in this case. Okay? All right, so that's electron notation. Electron notation. I want to talk a little bit about orbital diagrams. Another way to designate the position of electrons is the orbital diagram. Arrows are used to represent electrons, and an up arrow is spinning in one direction while a down arrow is spinning in the opposite direction. Okay? So I can use orbital diagrams like we've seen before, or I can use electron configuration. So here's a couple of elements, and you can check those on your own. All right? So let's take a look. Let's keep going. So this orbital diagram shows the boxes arranged in progressively increasing energy levels. Let's study this just a little bit. Fill in the appropriate boxes to show the correct orbital diagram for silicon. Now silicon has 14 electrons. Check that on your periodic table. So where do we put the first electron? We're going to put it right here. Not sure. Let me make my pen size just a little bit smaller. I think I can do that. Here we go. So one arrow going up, one arrow going down. Okay? And that's only 2. You've got a long way to go. One up, one down. Just like that. Now watch this. One up, one up, one up. Remember, Hund's rule says I have to put them in one into each of the sublevel, or one into each of the orbitals before I can put a second one in. So I've got 2 here, 2 more here. That's 4, 5, 6, 7, 8, 9, 10. Just like that. Remember, I'm going to silicon. So now I'm going to do 3s2. 3s2, just like that. Silicon had a total of 14 electrons. I've got 2, 4, 6, 8, 10, 12. Where do I put the next two? I'm going to put them right here. Watch. One here, one there. Okay? And that is the orbital diagram for silicon. All right? Great. We're moving at a good pace here. If you need to pause the video and kind of absorb this, that's fine. All right? So here we go. Let's increase this thickness again. It says noble gas configuration. What do we mean by noble gas configuration? For elements that have a lot of electrons, there's a shorthand notation called noble gas configuration. And here's how it works. You simply write the noble gas which precedes the element which you're interested in. Then write the electron configuration for the outermost or valence electrons. We've already said valence electrons are the outermost electrons. The table below shows a few examples, so let's try a few. Let's just take a look at, for example, beryllium. Beryllium has a total of 4 electrons. Follow me on your periodic table. A total of 4 electrons. So we write the noble gas configuration by going to the previous noble gas. So instead of writing, by the way, 1s2, 2s2, we're going to write a shorthand. The previous noble gas was helium. So we simply write helium in brackets just like this, and then write the last 2 electrons, in other words, the valence electrons after that. So it's helium in brackets, and then followed by 2s2. Magnesium, the previous noble gas to magnesium, let's see, is neon. So neon, we'll put in brackets, and then the last 2 electrons on the 3s energy level, so we'll say 3s2 after that. Calcium is previous noble gas is argon. So we'll put argon in brackets, and then the valence electrons are on the 4s main energy level, or the 4s energy level, so that would be 4s2, and so forth. And that is what we call noble gas configuration. Noble gas configuration. Let's take a look at a few odds and ends. And I tell you what, actually, I think this is a good place to finish this one. We'll do one more video, and that should do it for this unit. All right, I'll see you in the next one. Thanks. Bye-bye.